3I Atlas, discovered on July 1, 2025, by the NASA-funded Atlas Survey Telescope in Rio Hurtado, Chile, has captured global attention as the third confirmed interstellar object passing through our solar system. Unlike its predecessors, Oumuamua and 2I Borisov, 3I Atlas follows an extreme hyperbolic trajectory at a staggering speed of 58 kilometers per second, suggesting an origin far beyond our cosmic neighborhood. With a mysterious coma and tail forming as it nears the sun, scientists worldwide are racing to understand its unique characteristics and origins. Discovery of 3I Atlas. What if I told you that astronomers almost missed one of the most significant discoveries of the decade? On July 1, 2025, the Atlas telescope at Rio Hurtado, Chile, made the groundbreaking detection of 3Y Atlas, initially designated A11PL3Z. This faint object was discovered while moving at 61 kilometers per second through the dense star fields near the galactic center, close to the constellations Serpens Cauda and Sagittarius. The object was so faint at magnitude 18 that it was nearly invisible against the crowded background stars, requiring sophisticated computer algorithms to identify its movement against the stellar backdrop. Follow-up observations by professional and amateur astronomers worldwide confirmed its hyperbolic trajectory, marking it as the third known interstellar visitor after Oumuamua and 2I Borisov. Pre-discovery images from June 2025 later helped trace its path further back, with some observations dating to June 5, expanding scientists' understanding of this rare cosmic traveler. The discovery team immediately recognized the object's unusual motion and submitted their findings to the International Astronomical Union's Minor Planet Center, which initially listed it on the Near-Earth Object Confirmation page, until its true interstellar nature became clear through orbital calculations. Atlas Survey System. Have you ever wondered how we can spot something so small from billions of kilometers away? The Asteroid Terrestrial Impact Last Alert System, a network of telescopes designed to detect near-Earth objects, was pivotal in discovering 3Y Atlas. Operating 4 units globally, including 1 at the South African Astronomical Observatory and 2 in Hawaii, Atlas continuously scans the night sky for moving celestial bodies. Each telescope features a massive 7.4-degree field of view, about 15 times the diameter of the full moon, allowing them to survey enormous patches of sky quickly and efficiently. Equipped with powerful 50-centimeter telescopes and 110-megapixel CCD cameras, the system covers the sky rapidly, allowing early detection of objects like 3I Atlas even in challenging regions with dense star fields. Each Atlas unit can scan the entire visible sky once per night, taking exposures every 40 seconds, and observing each quarter of the sky 4 times nightly. This redundancy ensures that no fast-moving objects escape detection. The system processes thousands of images nightly, using advanced algorithms to identify moving objects against the stellar background. This revolutionary approach has transformed how quickly astronomers can identify and track new objects, proving essential for both planetary defense initiatives and groundbreaking scientific discoveries like interstellar visitors. Object classification and naming. Why does a single space rock get 3 different names, and what does each tell us about its nature? Upon discovery, the object was initially named A11PL3Z before gaining the official interstellar designation 3I Atlas. Scientists also assigned it the cometary name C/2025N1, reflecting its active nature as a true comet rather than an asteroid. The 3I designation officially marks it as the third confirmed interstellar object, following the naming convention established for 1 Oumuamua and 2I Borisov by the International Astronomical Union. Its orbit displays an eccentricity of about 6.14, far exceeding the threshold of 1.0 for bound solar orbits, confirming its interstellar origin beyond any doubt. This extreme orbital eccentricity is the highest recorded among all 3 known interstellar objects, making 3I Atlas's trajectory appear almost perfectly straight, rather than curved like typical comets. The Minor Planet Center announced the discovery on July 2, 2025, officially confirming its interstellar status after careful orbital analysis. This classification process involved multiple observations from telescopes worldwide to precisely determine the object's path and confirm that it originated from beyond our solar system. The naming reflects both its discovery survey and its unique characteristics as an active interstellar comet. Orbital characteristics. Imagine something moving so fast it makes a bullet look like it's standing still. 3. I-Atlas travels on a highly hyperbolic orbit with an incredibly high eccentricity of about 6.14, making its path almost a straight line past the Sun rather than the curved elliptical orbits typical of solar system objects. Its hyperbolic excess velocity measures around 58 kilometers per second, which is much faster than the previous interstellar objects Oumuamua at 26 kilometers per second and 2I Borisov at 32 kilometers per second. This tremendous speed ensures it's not bound by the Sun's gravity and will leave the solar system forever, never to return in human timescales. The comet's trajectory originates near the constellation Sagittarius, passing close to the galactic center, a region filled with dense star fields that made early detection extremely difficult. When discovered, 3Y Atlas was located 4.5 astronomical units from the Sun and moving at 61 kilometers per second relative to our star. Its orbital inclination is approximately 175 degrees, meaning it's traveling in a nearly retrograde direction compared to the planet's motion around the Sun. The comet will reach perihelion at about 1.35 astronomical units from the Sun, closer than Mars but farther than Earth. This close approach will significantly increase its activity levels, though unfortunately, it coincides with low solar elongation, making detailed observations challenging during its most active period. Physical properties. What makes this cosmic visitor so mysteriously elusive to measure accurately? Scientists quickly noticed that 3Y Atlas is an active comet with a fuzzy coma and a tail indicative of ongoing outgassing activity. Its true size remains uncertain due to this surrounding dust cloud that obscures the nucleus. But careful estimates suggest the nucleus is likely between 0.8 to 11 kilometers in diameter, with smaller sizes being more probable based on brightness measurements. Observations from prestigious telescopes like the Nordic Optical Telescope and the 2-meter twin telescope at Teide Observatory confirmed its brightness variations are remarkably small, less than 0.2 magnitudes over 29 hours of continuous monitoring. This stability suggests a relatively spherical shape or extremely slow rotation, contrasting sharply with Oumuamua's dramatic brightness changes that hinted at an elongated form. Further detailed analysis revealed a rotation period of approximately 16.79 hours, much slower than typical asteroids which often rotate in just a few hours. Its distinctly reddish color reflects dust composition similar to what was observed on 2I Borisov, pointing to complex surface materials rich in organic compounds. The comet's absolute magnitude of about h equals 12 to 13.7 helps astronomers estimate its size, though the active coma significantly complicates precise nuclear measurements. Unlike Oumuamua's highly elongated or potentially unusual shape, 3Y Atlas appears more conventionally spherical, resembling traditional comets in our solar system. Comet activity features. Ever seen a tail that points the wrong way and defies your expectations? The comet showcases intriguing activity patterns, including a faint coma, and a curious sunward-facing tail that appears as an anti-tail due to complex viewing geometry from Earth. David Jewett and Jane Liu, using the Nordic Optical Telescope on July 2, 2025, confirmed that 3Y Atlas was clearly active with a diffuse, measurable tail extending into space. The tail measures at least 25,000 kilometers long, as observed by Miguel R. Alarcón and his dedicated team at the Instituto de Astrofísica de Canarias through careful photometric analysis. The tail's unusual orientation suggests large, slow-moving micron-sized dust particles are being ejected preferentially along the comet's orbital plane, possibly from active cometary jets or indicating the nucleus might be a contact binary structure. During July 2025, the anti-tail appearance occurred because the tail pointed directly away from Earth's viewing angle, making it appear foreshortened and partially hidden behind the bright central coma. This sunward-facing tail phenomenon resembles those observed on other distant comets like C2014 UN-271, also known as Bernardinelli-Bernstein, indicating similar dust ejection mechanisms operating across different comet families. As 3I Atlas continues its approach toward perihelion, astronomers expect its activity to increase significantly, making the tail longer, brighter, and more visible from Earth, offering unprecedented insights into interstellar comet composition and internal structure. Amateur contributions. So, how can everyday stargazers help unlock cosmic mysteries? Well, the discovery of 3I/Atlas sparked an unprecedented worldwide collaboration between professional and amateur astronomers alike. Amateur astronomers, with mid to large backyard telescopes, contributed valuable time series photometry to study the comet's rotation and brightness variations. This global effort really complemented observations from major observatories, filling crucial gaps in data collection and, honestly, increasing observation frequency around the clock. Citizen scientists across Australia, Japan, and Chile began logging observations pretty much immediately after the discovery announcement. The collaboration was so extensive that an impromptu Slack channel with over 300 scientists buzzed continuously, coordinating observations and sharing real-time data. Amateur contributions were particularly valuable for rotation studies and continuous monitoring, since professional telescopes often have limited observation time. These kinds of partnerships showcased the remarkable power of community science in tracking fast-moving, faint celestial visitors. Even citizen science platforms like Zooniverse launched open campaigns to help analyze light curves and track the comet's behavior. This collaborative approach, honestly, represents the future of astronomy, where professional and amateur astronomers work together seamlessly to advance our understanding of rare cosmic phenomena. Surface composition. What secrets does the reddish glow of this cosmic wanderer reveal? Multi-wavelength observations revealed that 3I/Atlas has a distinctly reddish surface color, remarkably similar to the dust composition found on 2I Borisov and other distant comets. Spectroscopic studies using powerful telescopes like the Gran Telescopio Canarias showed a spectral slope of approximately 18% per 1,000 angstroms, indicating complex organic-rich dust particles. The comet's colors measured through various filters showed values of B-V equals 0.98, V-R equals 0.71, and other measurements that confirm its reddish nature. These findings suggest the comet's surface is coated in dark, carbonaceous material, possibly altered by cosmic rays during its lengthy interstellar journey spanning potentially millions of years. The reflectance spectrum shows consistent reddening across the entire wavelength range without significant absorption features, which is typical of primitive, carbon-rich materials. Observations from multiple telescopes, including the Falks Telescope North, confirmed that the coma had a reddish color indicative of dust, strengthening the case for organic compounds. This composition analysis provides crucial clues about the comet's formation environment and the conditions in its original star system, offering a direct sample of materials from beyond our solar system. Interstellar object density. Could our galaxy be teeming with cosmic nomads we've barely begun to discover? The detection rate of 3I/Atlas allows astronomers to refine estimates of interstellar object density in our galaxy with unprecedented precision. Based on Atlas's sky coverage and sensitivity capabilities, scientists calculate that objects of similar size may number approximately 1 per cubic astronomical unit in the solar neighborhood. This calculation assumes Atlas maintains 100% completeness for objects with apparent magnitude 19 or brighter, and factors in the survey's continuous monitoring capabilities. The discovery of 3 interstellar objects within just 8 years suggests these cosmic visitors might be far more common than previously thought, fundamentally reshaping our understanding of cosmic debris distribution throughout the Milky Way. Statistical models indicate that for every interstellar object we detect, hundreds or thousands more likely pass through unnoticed due to their faintness or unfavorable viewing geometry. The detection rate calculations help astronomers predict how frequently we might encounter such objects in the future. This new data hints that interstellar space contains a vast population of ejected planetary building blocks, failed planets, and other debris from stellar systems across the galaxy. Understanding this density is crucial for planning future interstellar object observation campaigns and estimating the total mass of material traveling between star systems. Origins and age speculation. Where in the vast cosmos did this ancient wanderer begin its journey? Based on its extraordinary velocity and trajectory, scientists speculate that 3I/Atlas may have originated from a distant star system millions of years ago, ejected during violent planetary formation processes. Its remarkable speed of 58 kilometers per second and unique path suggest it was gravitationally slingshot from its home system, possibly during interactions between forming planets or close stellar encounters. The comet's trajectory appears to originate from the direction of Sagittarius, near the galactic center, though this doesn't necessarily indicate its birth location due to the galaxy's rotation over cosmic time. Some researchers suggest 3I Atlas could be among the oldest known comets, potentially preserving pristine materials from the early universe. Its high velocity compared to other interstellar objects implies it may have traveled farther or been ejected more violently than Oumuamua or 2I Borisov. The comet's composition and activity patterns provide clues about conditions in its original stellar nursery, offering astronomers a rare opportunity to study materials formed around distant stars. These velocity-based age estimates help astronomers piece together the dynamic history of interstellar objects and their crucial role in galactic evolution, potentially carrying organic compounds and water between star systems across cosmic time. 3I Atlas continues to fascinate astronomers with its unique features and mysterious origins. As this third interstellar visitor speeds through our cosmic neighborhood at incredible velocities, humanity gains precious insights into the galaxy beyond our solar system. The collaboration between professional and amateur astronomers worldwide demonstrates the power of collective scientific exploration. Stay curious and keep exploring the wonders of space with Simply Science. Don't forget to like, share, and subscribe for more amazing facts and discoveries from the far reaches of the universe. Fresh observations of 3I Atlas are now shedding light on this mysterious interstellar visitor, and what scientists are discovering challenges everything we thought we knew about cosmic wanderers. With a trajectory that defies astronomical odds and behavior patterns unlike any natural object, this ancient visitor raises profound questions about its true nature. Could humanity be witnessing something far more extraordinary than just another comet? Discovery and initial detection. What if the most significant discovery in human history almost slipped past us unnoticed? 3I Atlas was discovered on July 1, 2025 by the Atlas telescope in Chile, initially receiving the mundane designation A11PL3Z before astronomers realized they were observing something unprecedented. This marks only the third confirmed interstellar object after Oumuamua in 2017 and Borisov in 2019, making it an extraordinarily rare cosmic event. The object had actually entered our solar system much earlier, but its challenging viewing angle near dense star fields delayed detection until it was already well within the inner solar system. Late detection meant crucial observation time was lost, similar to what happened with Oumuamua, when humanity missed the opportunity for detailed study. The discovery team quickly recognized unusual motion patterns that didn't match typical solar system objects, prompting immediate follow-up observations from telescopes worldwide. Within 24 hours, NASA confirmed its interstellar status, officially designating it as C/2025N1 and awarding it the historic 3Y designation. This rapid confirmation process demonstrated how much astronomical detection capabilities have improved since Oumuamua's controversial discovery 8 years earlier. Extraordinary orbital characteristics. How can an object's path through space defy the very laws of probability? 3I Atlas follows a hyperbolic orbit with an extreme eccentricity of 6.14, the highest recorded among all known interstellar objects, far exceeding Oumuamua's 1.2 and Borisov's 3.6. This incredible trajectory brings it racing through our solar system at 58 kilometers per second, making it the fastest interstellar visitor ever recorded. Most remarkably, its trajectory lies almost perfectly in the ecliptic plane, with astronomers calculating only a 0.2% probability of this occurring by random chance. The ecliptic alignment means the object travels along the same plane where all planets orbit, providing optimal viewing opportunities for studying multiple worlds during a single passage. This path appears deliberately designed for comprehensive planetary reconnaissance, rather than the random trajectory expected from a natural ejected object. The orbital mechanics suggest the object has maintained this precise alignment throughout its potentially millions-year journey through interstellar space. Such mathematical precision in trajectory raises fundamental questions about whether natural gravitational interactions could produce such an unlikely path. The combination of extreme speed, perfect ecliptic alignment, and record-breaking eccentricity creates a statistical anomaly that challenges conventional understanding of interstellar object behavior. Suspicious planetary encounters. What are the odds that a random space rock would visit exactly the planets most interesting to an alien intelligence? During its passage through our solar system, 3I Atlas approaches unusually close to Venus, Mars, and Jupiter, with astronomers calculating the probability of such precise planetary encounters at just 0.005%. The object passes within 0.65 astronomical units of Venus, 0.19 AU of Mars, and 0.36 AU of Jupiter, distances that would allow detailed study of each world's atmospheric composition, magnetic fields, and potential habitability. Perhaps most intriguingly, its closest approach to the Sun occurs precisely when Earth is positioned on the opposite side, blocked from direct observation during the most critical phase of its visit. Scientists estimate only a 7% probability that this solar eclipse timing would occur naturally. The trajectory resembles a carefully planned reconnaissance mission designed to gather maximum information about our solar system while minimizing detection risks. Each planetary encounter occurs at optimal distances for advanced sensors to collect detailed data without triggering obvious gravitational perturbations that might reveal artificial propulsion systems. The visiting pattern suggests intelligence rather than random cosmic wandering, following protocols that hypothetical alien explorers might use to study potentially inhabited star systems. This systematic approach to planetary surveys raises profound questions about the object's true purpose in our cosmic neighborhood. Physical properties and anomalies. How can something be simultaneously ancient beyond imagination, yet perfectly preserved for scientific study? Recent observations by the Vera C. Rubin Observatory reveal that 3I Atlas measures somewhere between 1 and 12 kilometers in diameter, making it, well, significantly larger than previous interstellar visitors, and potentially the biggest object of its kind ever observed. Age estimates suggest this cosmic wanderer is over 7 billion years old, predating our entire solar system and maybe even preserving materials from the early universe, back when galaxy formation was fundamentally different. Despite its extreme age, 3I Atlas appears remarkably well preserved, showing none of the expected degradation from billions of years of cosmic ray bombardment and micrometeorite impacts. The object exhibits the brightest absolute magnitude of any confirmed interstellar visitor, making it unusually reflective or possibly even internally illuminated compared to typical space debris. Its 29-hour rotation period with minimal brightness variation suggests either perfect spherical symmetry or an artificially stabilized spin rate, which really contrasts sharply with the chaotic tumbling you'd expect from natural ejected objects. The surface appears unusually smooth and uniform, lacking the irregular features you usually see on asteroids or comet nuclei shaped by countless impacts during interstellar travel. These physical properties create a profile more consistent with manufactured technology than natural formation, challenging scientists to explain how ancient materials could remain so pristine after eons of cosmic exposure. Comet-like features versus anomalous behavior. Why does this supposed comet behave unlike any other comet in recorded astronomical history? 3I Atlas displays a faint coma and a short tail measuring about 3 arcseconds, confirming active outgassing typical of comets approaching the Sun. Yet these features appear far more subdued than you'd expect for an object of its size and solar proximity. The coma appears compact and dense, rather than the diffuse, fuzzy appearance characteristic of normal comets, which suggests either an unusual composition or maybe even artificial containment of expelled materials. Most puzzling, the object lacks the prominent tail that should develop as it approaches perihelion, with only minimal dust ejection, despite receiving substantial solar heating. Spectroscopic analysis reveals water ice signatures, but the patterns just don't match expected models, with observed signals rising where theoretical predictions indicate they should actually drop. The outgassing appears controlled and limited, almost as if internal systems are regulating material release rather than allowing natural sublimation processes to proceed unchecked. Unlike typical comets that become increasingly active and chaotic as they near the Sun, 3I Atlas maintains remarkably stable behavior and appearance. The reddish coloration resembles outer asteroid belt objects more than pristine interstellar ice, suggesting complex surface processing or perhaps manufactured coating materials. These contradictory characteristics create a hybrid profile that fits neither pure comet nor asteroid classifications, demanding new explanatory frameworks for understanding interstellar visitors. Scientific debate: natural versus artificial. How do scientists reconcile extraordinary evidence with the burden of extraordinary proof? Professor Avi Loeb from Harvard University has publicly suggested that 3I Atlas could represent artificial technology, pointing to its statistically improbable trajectory, perfect timing, and anomalous physical properties as evidence warranting serious consideration of alien origins. Loeb argues that dismissing artificial possibilities without thorough investigation violates scientific methodology, especially when natural explanations fail to account for observed characteristics. However, many mainstream scientists dismiss these claims as irresponsible speculation that damages public trust in astronomical research and diverts attention from legitimate scientific study. Chris Lintott from Oxford University called the alien hypothesis nonsense, emphasizing that extraordinary claims require extraordinary evidence that simply doesn't exist. The debate centers on fundamental questions about scientific methodology. Should researchers explore all possible explanations, even seemingly outlandish ones, or maintain conservative approaches that prioritize conventional interpretations? Critics argue that entertaining alien explanations without definitive proof encourages conspiracy theories and undermines scientific credibility. Supporters counter that science advances by challenging assumptions and investigating anomalies that don't fit established models. This controversy reflects broader tensions within astronomy about how to balance open-minded inquiry with rigorous skepticism when confronting potentially paradigm-shifting discoveries. The scientific community remains divided on whether 3I Atlas deserves conventional analysis or represents something requiring entirely new investigative approaches. Spectral analysis mysteries. What secrets hide within the light signatures that challenge our understanding of interstellar chemistry? Spectroscopic observations using the Gemini S telescope and NASA IRTF reveal that 3I Atlas contains abundant water ice, but the spectral patterns, well, they exhibit puzzling characteristics that don't match theoretical models for natural comet composition. The optical spectrum shows about 10% reddening per 1,000 angstroms, which actually resembles D-type asteroids more than typical ice-rich comets. This suggests either some pretty unusual formation conditions, or maybe even artificial surface treatments. Moving on, the near-infrared analysis flattens to 3% per 1,000 angstroms, indicating large water ice grains. Yet the expected 1.5 micron water band is mysteriously absent, even though there are strong signals at other wavelengths. Scientists have managed to model the spectrum using 70% Tagish Lake meteorite material, combined with 30% water ice. But honestly, this composition seems inconsistent with objects formed in distant stellar systems billions of years ago. The spectral stability across 9 days of observation suggests remarkably uniform surface properties, which is in contrast to typical comets that show variable composition as different regions become exposed to solar heating. Color measurements through various filters confirm persistent reddish characteristics, indicating complex organic materials that could potentially preserve chemical signatures from alien star formation environments. However, the isotopic ratios and elemental abundances appear surprisingly similar to solar system materials, and that really raises questions about whether this truly represents pristine interstellar matter, or, well, something a bit more familiar. These spectroscopic puzzles demand new theoretical frameworks for understanding how interstellar objects preserve and modify their original compositions during million-year journeys through the galaxy. Dark forest hypothesis implications. Could 3I Atlas represent humanity's first encounter with the terrifying cosmic game theory known as the dark forest? This hypothesis suggests that intelligent civilizations throughout the universe remain hidden and silent, maintaining strict stealth protocols to avoid detection by potentially hostile species that might eliminate competitors before they become threats. 3I Atlas exhibits stealth-like behavior perfectly consistent with reconnaissance missions designed to study planetary systems while minimizing detection risks and exposure to defensive responses. The object's trajectory allows comprehensive solar system surveys while remaining hidden behind the sun during its most vulnerable closest approach, when any artificial systems would be most easily detected. Its deliberate timing ensures minimal observation opportunities during peak activity, following protocols that advanced civilizations might use for cautious exploration of potentially dangerous inhabited systems. The Dark Forest theory predicts that alien visitors would conduct rapid, efficient reconnaissance missions to assess threat levels and resource availability before deciding whether to establish contact, eliminate competition, or simply avoid detection entirely. 3. I-Atlas's behavior matches theoretical predictions for how intelligent species might approach unknown star systems, gather maximum information while maintaining escape routes and avoiding confrontation. The object's ancient age suggests it could represent technology from civilizations that achieved interstellar travel billions of years ago, when the galaxy was younger and potentially more hospitable to life. If this interpretation proves correct, humanity may be experiencing our first contact with alien intelligence, but contact designed to remain undetected until the visitors can assess whether we represent friends, enemies, or irrelevant primitives. Historical context and lessons. The arrival of 3I Atlas provides crucial insights gained from our previous encounters with interstellar wanderers and the opportunities we missed. When 1I Oumuamua was first spotted in 2017, the astronomical community was completely unprepared for studying such an extraordinary phenomenon. Robert Warwick, who made the discovery using the Pan-STARRS 1 telescope in Hawaii, has acknowledged how the object's swift departure left numerous fundamental questions permanently unanswered. The enigmatic acceleration that Oumuamua displayed without any visible cometary activity continues to baffle scientists today, demonstrating the critical importance of immediate and comprehensive observation protocols. 2 years later, Gennady Borisov discovered 2I Borisov from his private observatory in Crimea, giving astronomers a valuable second opportunity that was better managed but still limited by technological constraints. Mark Norris from the University of Central Lancashire has stressed that 3I Atlas represents our most significant chance yet to conduct thorough studies of an interstellar visitor, using cutting-edge instruments and globally coordinated observation campaigns. The enhanced detection systems of modern sky surveys, paired with instantaneous global communication networks, have enabled unprecedented real-time collaboration among observatories worldwide. These hard-learned lessons from previous interstellar encounters have fundamentally transformed how the scientific community approaches these exceptionally rare cosmic events. Future observations and implications. Will the next few months provide humanity with definitive answers about 3I Atlas's true nature, or deepen the mystery forever? Perihelion, on October 30, 2025, offers scientists their best opportunity to conduct comprehensive analysis before the object begins its final departure from our solar system. Multiple telescopes worldwide are coordinating unprecedented observation campaigns using every available technique, from radio astronomy to gravitational wave detection, ensuring no potential evidence escapes analysis. The object will re-emerge from behind the Sun in December 2025, providing a final observation window to confirm or refute artificial origin theories before it disappears into interstellar space forever. Advanced space missions including MAVEN, Mars Reconnaissance Orbiter, and the Jupiter Icy Moons Explorer will attempt close-range observations during planetary encounters, potentially revealing surface details impossible to detect from Earth. Scientists are developing new analytical techniques specifically designed to distinguish between natural and artificial objects, creating frameworks that will guide evaluation of future interstellar visitors. The comprehensive data collection from 3I Atlas could revolutionize understanding of interstellar object populations, formation mechanisms, and the potential prevalence of alien technology in our galactic neighborhood. These observations will either definitively prove 3I Atlas is a natural comet, ending speculation about artificial origins, or provide evidence that fundamentally changes humanity's understanding of our place in the universe. The implications extend far beyond astronomy, potentially affecting planetary defense strategies, international space cooperation, and humanity's long-term preparation for contact with alien intelligence. Future detection systems are being designed to identify similar objects much earlier, providing years rather than months for detailed study and potential interaction. As 3I Atlas continues its enigmatic journey through our solar system, scientists race against time to unlock its secrets before it vanishes forever. Whether this ancient visitor proves to be a natural relic from distant stars or something far more extraordinary, Its discovery marks a pivotal moment in humanity's cosmic awareness. The truth about 3I Atlas may reshape our understanding of life, intelligence, and our place in the universe. Stay curious about the cosmos with Simply Science. Like, share, and subscribe for the latest discoveries from the edge of human knowledge. When mysterious objects like 3I Atlas streak through our solar system, how do scientists determine if they're natural space rocks or, something far more extraordinary? The process of distinguishing between cosmic debris and potential alien technology involves rigorous scientific methods, advanced telescopes, and careful analysis of physical properties. From spectral signatures to orbital mechanics, astronomers have developed sophisticated techniques to separate fact from fiction in the search for extraterrestrial intelligence. A rare visitor from deep space. What makes an object suspicious enough to warrant investigation for potential alien origins? When astronomers discovered 3I Atlas in July 2025, they immediately began analyzing its characteristics using established protocols for identifying unusual celestial visitors. The object's extreme velocity of 58 kilometers per second and hyperbolic trajectory initially raised questions about its nature, similar to how Oumuamua sparked scientific debate in 2017. Scientists look for specific markers that distinguish natural objects from potential artificial constructs, including surface composition, structural integrity, and behavioral patterns. Natural interstellar objects typically display predictable properties based on their formation in distant stellar systems, while hypothetical alien technology might exhibit anomalous characteristics that defy conventional physics. The key lies in systematic observation and measurement rather than speculation. Professional astronomers use multiple independent observation methods to verify their findings and eliminate human error or equipment malfunction. Every mysterious space object receives the same rigorous scientific scrutiny, ensuring that extraordinary claims require extraordinary evidence. This methodical approach has successfully identified thousands of natural objects while maintaining vigilance for genuinely anomalous discoveries. The scientific community remains open to finding evidence of alien technology while maintaining strict standards for verification and peer review. The breaking discovery. How do scientists separate genuine discoveries from false alarms when studying mysterious space objects? The confirmation process begins immediately after initial detection, involving multiple independent observations from different telescopes worldwide. When Atlas telescopes first spotted 3I Atlas, teams at observatories across Chile, Hawaii, and South Africa began collecting data to verify its properties and trajectory. Scientists analyze orbital mechanics first, determining whether an object follows natural gravitational physics or exhibits unexplained acceleration patterns that might suggest propulsion systems. Spectroscopic analysis reveals surface composition, helping distinguish between rocky, icy, or metallic materials that provide clues about natural versus artificial origins. The object's rotation rate, brightness variations, and thermal emissions undergo careful scrutiny to identify any anomalies inconsistent with natural formation processes. Professional astronomers coordinate through international networks, sharing data and cross-referencing observations to eliminate observational errors or equipment malfunctions. The International Astronomical Union maintains strict protocols for announcing discoveries, requiring multiple confirmations before official designation. Scientists also consider alternative explanations for unusual properties, exploring whether natural phenomena could account for seemingly anomalous characteristics. This systematic approach ensures that only genuinely unexplained objects receive serious consideration as potential evidence of alien technology, while protecting the scientific community from premature or inaccurate conclusions that could damage public trust in astronomical research. The discovery story. What specific techniques do astronomers use to analyze potentially artificial objects in space? The investigation process relies heavily on photometry, spectroscopy, and astrometry to build comprehensive profiles of mysterious visitors. David Jewett and Jane Liu, pioneers in studying distant solar system objects, established many protocols now used for interstellar object analysis. Scientists measure brightness variations over time, looking for rotation patterns that might indicate artificial symmetries or unusual structural properties inconsistent with natural formation. Spectral analysis reveals elemental composition by examining how objects absorb and reflect different wavelengths of light, providing chemical fingerprints that distinguish manufactured materials from natural rock, ice, or metal. Thermal imaging detects heat signatures that might indicate internal power sources, active machinery, or artificial temperature regulation systems. Radio telescopes scan for electromagnetic emissions that could signal communication systems, navigation equipment, or other technological signatures. High-resolution imaging attempts to resolve surface features, searching for geometric patterns, artificial structures, or manufacturing marks that would distinguish technology from natural geological processes. Scientists also monitor for trajectory changes that might indicate course corrections, propulsion systems, or intelligent navigation, rather than purely gravitational motion. The Very Large Array and other radio telescope networks continuously monitor for signals from objects of interest. Modern computational power allows rapid analysis of vast datasets, enabling scientists to process observations from multiple wavelengths simultaneously and identify subtle anomalies that might escape individual telescope observations. A stranger in our midst. So, how do natural objects behave differently from potential alien artifacts when observed through powerful telescopes? Well, natural interstellar objects typically show predictable characteristics, based on their formation environments and the effects of cosmic ray exposure during their really long journeys through space. Asteroid composition usually follows known patterns, rocky, metallic, or icy materials that are consistent with planetary formation processes around distant stars. Scientists expect natural objects to display signs of space weathering, like surface darkening from cosmic ray bombardment and micrometeorite impacts that build up over millions of years. Their rotation rates generally fall within ranges determined by gravitational interactions during ejection from their parent star systems, and these are typically measured in hours, not artificially precise periods. When it comes to comets, natural outgassing produces predictable chemical signatures as volatile materials sublimate while approaching the sun, creating those characteristic coma and tail formations. The structural integrity of these objects follows physical laws, how different materials respond to gravitational stresses, temperature swings, and rotational forces during interstellar travel. Scientists use computer models to predict how various natural materials would appear after extended exposure to cosmic radiation and extreme temperatures in interstellar space. On the other hand, artificial objects might show unusual geometric shapes, precise rotational periods, unexpected material compositions, or surface features that just don't line up with natural formation processes. The Spitzer Space Telescope and other infrared instruments can detect thermal anomalies, which might hint at internal power sources or artificial heating systems. And with advanced imaging techniques, researchers examine surface textures, searching for manufacturing marks, geometric patterns, or structural elements that would suggest intelligent design rather than natural geological or impact processes. The predecessors. What lessons did scientists learn from previous mysterious objects that shaped current investigation protocols? The 2017 discovery of Oumuamua really changed the game for astronomers, establishing comprehensive analysis frameworks that are still in use today. Robert Warwick at the University of Hawaii was the first to detect Oumuamua, which showed unusual acceleration patterns that initially puzzled scientists until natural explanations involving outgassing were confirmed. The controversy over Oumuamua's elongated shape and slight acceleration taught researchers the importance of gathering multiple types of observational data before jumping to conclusions. Avi Loeb from Harvard University suggested considering artificial origins for Oumuamua, which sparked important discussions about scientific methodology and the burden of proof needed for extraordinary claims. Then there was 2I/Borisov, discovered in 2019 by amateur astronomer Gennady Borisov, which provided a more conventional example of an interstellar comet with clearly natural characteristics. These experiences established standard protocols for studying interstellar objects, like immediate spectroscopic analysis, trajectory monitoring, and international coordination for follow-up observations. Scientists learned to consider both natural and artificial explanations at the same time, while maintaining rigorous standards for evaluating evidence. The experiences with these objects also highlighted the need for rapid response capabilities, since interstellar visitors are only observable for limited time periods before they leave the solar system. Nowadays, modern protocols include automated alert systems that notify astronomers worldwide within just a few hours of discovery, enabling coordinated international observation campaigns to maximize data collection from these rare cosmic visitors. The cosmic journey. How do orbital mechanics help scientists distinguish between natural objects and potential alien spacecraft? Well, natural interstellar objects follow predictable trajectories determined by gravitational interactions with the sun and planets, while artificial objects might show unexplained course corrections or propulsion signatures. Gravitational physics gives us precise mathematical frameworks for calculating expected paths, allowing scientists to spot any deviations that could indicate active navigation systems. For example, the trajectory of 3I/Atlas follows a hyperbolic orbit with an eccentricity of 6.14, which is totally consistent with natural ejection from a distant star system millions of years ago. Scientists use sophisticated computer simulations to trace backward trajectories, trying to identify possible origin star systems and validate natural formation scenarios. Of course, unexpected acceleration or deceleration patterns might indicate propulsion systems, though natural phenomena like outgassing can also cause trajectory changes in comets and asteroids. JPL's navigation teams keep a close watch on object trajectories using radar and optical observations, measuring positions with extraordinary precision to catch even the subtlest motion anomalies. Artificial objects could show perfect geometric flight paths, precise timing and trajectory changes, or acceleration patterns that just don't fit with known natural forces like solar radiation pressure or gravitational slingshot effects. The Deep Space Network offers radar tracking capabilities that can pick up tiny changes in velocity or trajectory that optical telescopes might miss. Scientists also analyze how objects respond to solar radiation pressure, gravitational perturbations from planets, and other natural forces, just to make sure their motion follows purely physical laws, or to see if it hints at intelligent control systems managing their flight paths through the solar system. A scientific goldmine. What advanced technologies enable scientists to determine if mysterious objects are natural or artificial? Well, modern astronomical instruments provide, honestly, unprecedented capabilities for analyzing the physical properties and behavior of potential alien artifacts versus natural space debris. Spectroscopic analysis, using instruments like those on the James Webb Space Telescope, can identify specific chemical compositions, revealing whether objects contain materials consistent with natural formation or, unusual artificial alloys. High-resolution imaging from ground-based adaptive optic systems and space telescopes can resolve surface features as small as tens of meters, searching for geometric patterns, manufacturing marks, or structural elements that would indicate intelligent design. Radio astronomy facilities like the Very Large Array continuously monitor for electromagnetic emissions that might indicate communication systems, navigation equipment, or other technological signatures from mysterious objects. Infrared observations detect thermal signatures that could reveal internal power sources, artificial heating systems, or temperature regulation inconsistent with passive solar heating of natural materials. Advanced computer modeling allows scientists to simulate how various materials and structures would behave under different conditions, comparing observations with theoretical predictions for natural versus artificial objects. Gravitational wave detectors provide additional monitoring capabilities for massive objects that might employ, say, exotic propulsion systems. Machine learning algorithms process vast amounts of observational data, identifying subtle patterns and anomalies that might escape human analysis. And finally, international coordination through networks like the International Astronomical Union ensures that multiple independent teams analyze the same objects, reducing the risk of observational errors or biased interpretations that could lead to false conclusions about potential alien technology. Unanswered questions. What specific characteristics would definitively identify an object as alien technology rather than natural space debris? Scientists have established clear criteria for distinguishing artificial constructs from natural celestial objects, though, some borderline cases continue to challenge conventional analysis methods. Geometric precision in shape, surface features, or rotational periods would strongly suggest intelligent design, since natural processes rarely produce perfectly symmetrical or mathematically precise structures. Unusual material compositions containing pure metals, artificial alloys, or isotopic ratios inconsistent with stellar nucleosynthesis would indicate manufacturing rather than natural formation processes. Active electromagnetic emissions, especially coherent radio signals or structured data transmissions, would provide compelling evidence of technological origin and possibly intelligence. Propulsion signatures including unexplained acceleration, trajectory corrections or energy emissions inconsistent with known natural forces would suggest artificial control systems. Surface features showing clear geometric patterns, construction joints or manufacturing marks visible through high-resolution imaging would distinguish technology from natural geological processes. Internal structure revealed through radar or gravitational analysis might show artificial compartments, machinery, or organized systems rather than homogeneous natural composition. Thermal anomalies indicating internal power sources, temperature regulation, or waste heat disposal would suggest active technological systems rather than passive solar heating. Response to external stimuli, such as changes in behavior when approached by spacecraft or exposed to radio signals, might indicate artificial intelligence or automated systems. The SETI Institute maintains protocols for evaluating potential techno-signatures, requiring multiple independent confirmations before announcing discoveries of artificial objects. Scientists continue refining detection methods and analysis techniques to ensure they can recognize genuine alien technology while, avoiding false positives from natural phenomena. The alien question. How do scientists balance open-minded investigation with rigorous skepticism when evaluating potential alien artifacts? The scientific method requires maintaining both receptivity to extraordinary discoveries and strict evidential standards that prevent premature conclusions about alien technology. Avi Loeb, chair of Harvard's astronomy department, advocates for seriously considering artificial origins when natural explanations prove inadequate, while emphasizing the need for extraordinary evidence to support extraordinary claims. Carl Sagan's famous principle that extraordinary claims require extraordinary evidence guides most astronomical investigations, ensuring that potential alien discoveries undergo the most rigorous peer review and verification processes. Scientists recognize that discovering genuine alien technology would represent one of humanity's most significant achievements, requiring absolute certainty to avoid false announcements that could damage scientific credibility. The SETI Institute has developed comprehensive protocols for evaluating potential techno-signatures, including multiple independent verification requirements and international coordination before making public announcements. Natural explanations must be thoroughly explored and eliminated before considering artificial origins, as the history of astronomy shows that apparently anomalous objects often have conventional explanations discovered through continued observation. Peer review processes ensure that multiple independent scientists analyze the same data and observations, reducing the risk of individual bias or analytical errors that might lead to incorrect conclusions. The scientific community maintains healthy skepticism while remaining genuinely open to discovering evidence of alien technology, balancing the need for rigorous investigation with the recognition that such discoveries would profoundly impact human understanding of our place in the universe and the prevalence of intelligent life throughout the galaxy. Dawn of a new era. What does the future hold for detecting and analyzing potentially artificial objects in our solar system? Technological advances in astronomy continue revolutionizing our ability to identify, track, and study mysterious visitors that might represent alien technology rather than natural space debris. Next-generation telescopes like the Vera Rubin Observatory will survey the entire visible sky nightly, dramatically increasing discovery rates for interstellar objects and providing rapid alerts for international follow-up observations. Advanced artificial intelligence systems will analyze observational data in real time, identifying subtle anomalies and patterns that might escape human attention, while flagging objects requiring immediate investigation. Space-based observation platforms will provide continuous monitoring capabilities without atmospheric interference, enabling detailed spectroscopic and thermal analysis of potentially artificial objects throughout their solar system passages. Improved international coordination through organizations like the International Astronomical Union ensures rapid information sharing and coordinated observation campaigns that maximize data collection from rare interstellar visitors. Radar astronomy facilities continue expanding their capabilities for detailed trajectory tracking and surface mapping, providing unprecedented precision in detecting artificial structures or unexpected motion patterns. Future space missions might include dedicated interceptor spacecraft designed to rendezvous with mysterious objects for close-range analysis, collecting samples and detailed measurements impossible from ground-based observations. The Breakthrough Listen project and similar initiatives continue expanding radio monitoring capabilities, searching for electromagnetic signatures that might indicate technological origins. Enhanced computer modeling and simulation capabilities will enable more sophisticated analysis of observational data, comparing observations with theoretical predictions for both natural and artificial objects to distinguish between conventional explanations and genuinely anomalous discoveries requiring extraordinary investigation. The search for alien technology requires balancing scientific rigor with open-minded investigation, ensuring we don't miss genuine discoveries while avoiding false alarms. As our detection capabilities advance, astronomers remain vigilant for objects that might represent humanity's first contact with extraterrestrial intelligence. Every mysterious visitor gets the same careful analysis, protecting both scientific credibility and our readiness for extraordinary discoveries. Keep exploring the cosmos with Simply Science, like, share and subscribe for more fascinating insights into our universe's greatest mysteries. It started as nothing more than a flicker, barely a whisper in the data streams flowing from observatories around the world. But when James Webb Space Telescope captured its first detailed image of the mysterious interstellar visitor 3Y Atlas, scientists realized they were witnessing something that could rewrite our understanding of the cosmos. This ancient traveler from beyond our solar system carries secrets that challenge everything we thought we knew about space. The flicker in the dark. The discovery of 3Y Atlas started, not with a bang, but with a faint cosmic flicker detected by the Atlas telescope at Rio Hurtado, Chile in early July 2025. Astrophysicist Matthew Payne at the Minor Planet Center was among the first to flag its interstellar trajectory, confirming that what began as a whisper in Atlas survey data was unlike anything bound to our sun. Days later, a global alert went out to observatories worldwide, and research teams coordinated with NASA's JWS team to track this mysterious visitor. This collective effort led to the crucial moment when NASA released its first image, ultra-detailed and definitive, immediately captivating Dr. Payne's team and the world's top interstellar object researchers. The initial detection required sophisticated computer algorithms to distinguish the object's movement against the crowded stellar background near the constellation Sagittarius. Multiple observatories confirmed the unusual motion patterns within 48 hours, establishing international protocols for rapid follow-up observations. The discovery highlighted how advanced survey systems have revolutionized our ability to detect cosmic visitors that would have remained invisible just decades ago. Beyond the solar veil. Pinpointing the origin, the Atlas team led by Larry Deneau confirmed 3Y Atlas's interstellar status, distinguishing it by its hyperbolic excess velocity well above the escape velocity from the Sun. Analysis by Dr. Karen Meach, who also characterized Oumuamua, showed the orbital data marked its point of entry far above the ecliptic, entering from deep space. Observatories from the European Southern Observatory to Mauna Kea, Hawaii, contributed positional data that painted a picture of an object traveling for potentially millions of years through interstellar space. These collaborative efforts proved this was the third object after Oumuamua and Borisov to have entered from outside the solar system, sparking a fast-tracked global campaign to track and analyze it before it disappeared forever. The object's trajectory suggested it had been wandering the galaxy for eons, carrying pristine materials from its unknown stellar birthplace. International astronomers worked around the clock to maximize observation time, knowing that such visitors offer rare glimpses into the composition and conditions of distant star systems. The coordinated response demonstrated how the astronomical community has learned from previous missed opportunities with earlier interstellar visitors. The accelerating mystery. Why does 3I Atlas exhibit velocity patterns that fundamentally challenge our understanding of celestial mechanics? Scientists conducting comprehensive trajectory analysis have discovered that this enigmatic interstellar visitor displays acceleration characteristics completely unlike typical comets or asteroids native to our solar system. While most celestial objects follow precisely predictable orbital paths determined exclusively by gravitational influences from the Sun and planets, 3I Atlas demonstrates subtle yet scientifically significant deviations from all expected trajectories based on conventional physics models. These anomalous acceleration patterns strongly suggest that forces extending far beyond simple gravitational attraction are actively influencing its motion through space, in ways that current astrophysics cannot fully explain. The object's peculiar behavior bears striking resemblance to that of one Oumuamua, which famously displayed mysterious non-gravitational acceleration that completely baffled the global scientific community and sparked intensely controversial theories about possible artificial origins. Early observational data revealed 3 I Atlas beginning active cometary outgassing while still positioned 4.5 astronomical units from the Sun, a distance much greater than where typical solar system comets begin their characteristic, volatile sublimation processes. This remarkably early activation, combined with its highly unusual velocity profile and trajectory characteristics, creates an accelerating scientific mystery that fundamentally challenges conventional theoretical models of cometary physics and interstellar object behavior. The extraordinary combination of extreme hyperbolic velocity, unprecedented trajectory parameters, and completely anomalous acceleration signatures has forced astronomers worldwide to seriously reconsider fundamental assumptions about how interstellar objects behave when passing through alien star systems, opening entirely new avenues of research into the complex dynamics governing these mysterious cosmic wanderers. Patterns in the void. The intrigue deepened when the Vera C. Rubin Observatory Analysis Group, led by Dr. Zdenka Vokrulicki, noted a trend in the frequency of interstellar objects visiting our solar system. Since the surprise of Oumuamua in October 2017 and 2I/Borisov in December 2019, detection rates have steadily increased, thanks to improved survey technology and, better international coordination. The International Astronomical Union actually convened a special panel to discuss the implications for galactic object exchange, stressing that the regular arrival of such bodies really challenges previous models of solar system isolation. Each confirmed object, now that's 3 in under a decade, forces a rewriting of our assumptions about material drifting between stars and the dynamic nature of our galactic neighborhood. Statistical analysis suggests that thousands of similar objects pass through the outer solar system undetected each year, representing a vast population of interstellar wanderers. The pattern indicates that our solar system sits within a stream of cosmic debris ejected from stellar systems throughout the Milky Way galaxy. And advanced detection capabilities promise to reveal many more such visitors, fundamentally changing our understanding of how matter moves between star systems and the frequency of interstellar exchanges. The machine hypothesis. New Webb imagery processed by the Space Telescope Science Institute in Baltimore and interpreted by a multidisciplinary panel led in part by Dr. Avi Loeb, set off debate on possible artificial origins. Loeb highlighted unexpected geometry in the object right-angle reflectivity patterns and non-random surface features that seemed inconsistent with natural formation processes. The European Space Agency's JWST spectroscopy division found thermally anomalous regions and odd shadowing that defied conventional models of cometary behavior. Team member Dr. Heidi Hamel, planetary scientist and JWST co-investigator, cautioned that such findings don't yet confirm technology, but the conversation around the machine hypothesis went global after unexpected press releases. The object's surface appeared remarkably smooth and uniform, lacking the irregular features typical of natural space debris that's been battered by cosmic rays and micrometeorites during interstellar travel. Advanced imaging revealed geometric patterns that some researchers interpreted as possible structural elements, though others argued these could result from unusual crystallization processes during the object's formation. The debate really highlighted the challenges of distinguishing between natural and artificial characteristics when examining objects from unknown stellar environments with, potentially different formation conditions. Spectral secrets. Spectroscopic data from the James Webb NIRSpec instrument showed 3I/Atlas contains unfamiliar mixtures of organics, silicates, and metallic alloys, not typical for solar system comets. Dr. Alan Fitzsimmons from Queen's University Belfast identified a significant absorption at 1.5 microns, associated with hydrated minerals, alongside anomalous emission lines unexplained by water or carbon dioxide alone. NASA's Goddard Space Flight Center provided confirmation, reporting faint but consistent microwave emissions that suggested active internal processes. Dr. Jessica Agarwal from the German Aerospace Center noted These combined features could suggest prior irradiation or artificial alteration of native ices, fueling both natural and technological hypotheses about the object's origin. The spectral signatures revealed isotopic ratios that differed from typical solar system materials, indicating formation in an environment with different stellar nucleosynthesis products. Rare Earth elements appeared in concentrations that challenged existing models of planetary formation and cometary composition. And the presence of complex organic molecules typically associated with biological processes sparked additional speculation, though researchers emphasized that such compounds can form through natural chemical processes in interstellar space. The information blackout. So, amid mounting discoveries, global scientists started to notice restricted access to JWST raw data beginning on August 18, 2025. Dr. Joseph Maciero of the Planetary Defense Coordination Office testified that agency data review protocols were now being applied to 3I/Atlas, and he cited national security as the reason for limiting information sharing. Meanwhile, SETI Institute researchers, led by Dr. Jill Tarter, raised open letters demanding transparency, and the European Space Agency's Gaia mission team quietly shared independent astrometry with their international colleagues. Tensions really flared during an American Astronomical Society session, when international collaboration took a back seat to agency security reviews. This just revealed the growing friction between open science and government oversight on cosmic anomalies. Scientists expressed a lot of frustration that crucial observation windows were being compromised by bureaucratic delays and, honestly, classification concerns. The controversy really highlighted some fundamental questions about who controls access to cosmic discoveries and whether potential extraterrestrial contact should be subject to governmental secrecy. In response, international researchers began developing independent observation networks to ensure that scientific data would remain accessible to the global community, regardless of individual government policies regarding space-based discoveries and their potential implications for national security. Controlled heat and hidden intent. Thermal mapping using Webb MIRI instruments, supervised by Dr. Michael Werner at JPL, exhibited these adaptive temperature zones across the object's surface, which honestly is not something you see in typical comets. Dr. Christina Thomas at Northern Arizona University presented findings of synchronous heat regulation, and that really stands out, especially when you compare it to the chaotic surface cooling we've seen on icy nuclei, like 67P Churyumov-Gerasimenko. Now, key data obtained near perihelion on August 19, 2025, revealed the stabilization of energy emission regions that actually seemed to respond intelligently to solar heating. Theorist Dr. Gregory Laughlin at Yale even hypothesized that such signatures might imply, quote, thermal shielding or technology for intent-driven adaptation, a radical but now openly discussed possibility among planetary scientists. The temperature control followed these predictable patterns that maintained optimal conditions for preserving internal structures, and that honestly suggests either remarkable natural adaptation or deliberate engineering. Computer models showed that natural processes alone just couldn't account for the precision of thermal regulation observed across different surface regions. What's even more surprising is that the controlled heating patterns persisted, even as the object moved through varying solar radiation intensities, indicating active, rather than passive, thermal management systems that really defy our conventional understanding of cometary physics. The prime number message. Analysis teams at the Max Planck Institute for Radio Astronomy, led by Dr. Michael Kramer, detected heat emission modulations that, after Fourier transformation, revealed repeated prime number sequences embedded in the thermal output. Dr. Sophia Sheikh, a SETI researcher, independently validated a 17-23-31 pattern in night-to-night thermal variations using Green Bank Observatory data and, some pretty sophisticated signal processing techniques. This prime encoding is considered by scientists, as originally argued by Carl Sagan, to be the most likely signal structure used by non-human intelligences trying to communicate across interstellar distances. The findings, if verified by international SETI groups, could actually represent the first candidate evidence for information intentionally encoded in a celestial object passing through our solar system. The mathematical sequences appeared with statistical significance far exceeding random thermal fluctuations, suggesting deliberate modulation of heat emission patterns. Multiple independent verification attempts confirmed those prime number sequences across different observation periods and wavelengths. The discovery prompted emergency sessions at SETI institutes worldwide, as researchers grappled with the possibility that, just maybe, humanity had detected its first confirmed extraterrestrial communication attempt, though, of course, skeptics continued to search for natural explanations. The Watchers and the Watched. With the International Astronomical Union's special session, the world watched as experts like Dr. Lisa Kaltenegger from Cornell, astrobiologist Dr. Sarah Seeger, Planetary Protection Officer Dr. Catherine Conley, and SETI pioneer Frank Drake reflected on the profound implications of these discoveries. The paradigm has fundamentally shifted. The idea that humanity is the primary watcher of the cosmos has, well, inverted, with 3I Atlas representing potential evidence that we ourselves are being observed and studied. This reversal sparks some really intense debate about whether ethical and existential responsibilities should ever be confirmed, especially with direct, possibly intentional signatures detected in a passing interstellar visitor. The story of 3I Atlas will shape cosmic policy, philosophy, and planetary science for decades to come as humanity grapples with its changing role in the universe. Scientists are now developing new protocols for handling potential extraterrestrial contact scenarios, recognizing that traditional assumptions about human cosmic isolation may no longer apply. The discovery has prompted philosophical discussions about humanity's readiness for contact with advanced civilizations and the implications of being observed by intelligence that may have been studying Earth for extended periods. International cooperation frameworks are being established to ensure unified responses to future encounters with potentially artificial interstellar objects. The first real image from the James Webb Space Telescope begins a bold chapter in cosmic history. As data pours in and global teams compete and cooperate across boundaries, 3I Atlas stands as both a scientific puzzle and a reminder of our shared curiosity about the universe. The search for answers continues to accelerate with each new discovery. Keep exploring the cosmos with Simply Science. Like, share, and subscribe for our next cosmic revelation.